Peace be upon you, and God's mercy and blessings. In the last lecture, we saw together how we were able to use the bias differential relay to protect equipment like transformers, and how we managed to overcome the challenges we faced by using matching current transformers, through which we were able to perform current value adaptation, zero sequence current handling, in addition to vector group adaptation. In this lecture, we want to see together how the transformation occurred from electromechanical relays to numerical relays. Here, we want to talk about two things. Number one, the transformer differential system, and number two, the transformer differential characteristics. The first thing we have is the numerical relay transformer differential system. Let's now assume that we have a transformer, and this transformer consists of two sides. The transformer vector group can be dyn, ynd, dd, or yn, and here we have a vector group number from 0 to 12. This transformer can be step up or step down, meaning in the end we will have an upstream and a downstream. Okay, let's now say that we have only one breaker on each side of the transformer, and therefore we will have only one CT, current transformer, on each side of the transformer. In this case, we need a numerical relay, B, that contains two CT inputs, so that the CT on the high voltage side of the transformer is connected to one CT input of the two CT input numerical relay, and the CT on the low voltage side of the transformer is connected to the second CT input in the numerical relay. So, how will the connection be? The connection will be like this. We will notice the following here. First, the terminals facing the transformer on both sides of the transformer are connected together to form the star point. As for the other terminals, which are on the bus bar side and not facing the transformer on both sides of the transformer, they are connected to the dot point in my numerical relay. Therefore, in this case, as we briefly mentioned, your star point is towards the protected object, and the external terminals are connected to the dot point of the relay, meaning the polarity setting is towards the protected object. You can refer back to the lecture that will appear for you now, where we discussed in detail the concept of connecting the current transformer to the protection relays, or the numerical protection relays. Very good. Now, the currents that have entered the numerical relay are in amperes. So will I take these currents and deal with them directly, meaning will I add them together or subtract them from each other and then calculate the transformer differential and the transformer restrained and so on? Differential with the transformer and so on? Of course not. So what will I do? The first thing is that when the frequency enters the numerical relay performs something called current value adaptation. What does current value adaptation mean? This is a method used by the numerical relay by utilizing what is called the per unit value or the percentage value, so that it matches the current magnitude. Matching for the current magnitude. Then the relay performs something called vector group adaptation, B, and I0 handling, and this is done through what is called the compensation matrix. The compensation matrix is a 3x3 matrix and depends on the vector group number of the transformer. Finally, the values obtained from both sides of the transformer are taken and applied to the transformer differential characteristics, regardless of their form, which varies from one protection relay to another. Of course, we will discuss each of these aspects in detail in the upcoming lectures. The second thing we have is the transformer differential characteristics in numerical relays. Transformer differential characteristics is the relationship between the differential current, which is the vectorial summation of currents, or the directional sum of the currents, the high voltage side current and the low voltage side current, the directional sum of the currents of the high voltage side and the low voltage side and the low voltage side current. Very nice. And the algebraic sum of the currents, or the algebraic sum on both. Well, we will notice here that the directional sum of the currents means that it hasn't changed from even. meaning that the differential equation remains unchanged. But what changes for you is the algebraic sum of the currents or the algebraic sum on both. Well, as long as it doesn't depend on the angles, and as long as it doesn't depend on the directionality of the current, and depends only on the magnitude, then I can consider it as representing how much current is flowing in my system, in my transformer or system, or how much my loading conditions are. Okay, let's go back again. When we had Mertz price, we agreed that it faced a set of challenges during the different operating conditions, and we solved them using the bias differential. Let's see how we will solve them using the numerical relay. So, when did you face these challenges? You faced them in the different operating conditions. In the different operating conditions, the operating condition was based on the load. Okay, and now you told me that the bias or astern or stabilization will represent the load for you. So I can consider that from the beginning of 0 to a certain point it represents for you no load or light load condition. So now, or the light load condition, meaning now this axis of the bias or strain has become, for me, representing the loading condition. The first part of it is the no load or light load condition. Then, if the currents increase more than that, it represents the loading and overloading condition for me. Then, if the currents increase beyond that, it represents the heavy load and external fault condition for you. Very nice. Okay. When we go back to the beginning, it means that there is one breaker closed on one side of the transformer and the other breaker is open. Therefore, you have a load on the transformer. There might be a load on the cable that goes to the transformer, and so on. All these currents are read from one side of the transformer, and the other side will not be reading any currents. In addition to the light load condition, it means that the transformer is loaded at a small percentage, let's say 10 to 15, 20%, of its full load current. Consequently, a ratio error starts to appear between the two sides of the transformer, which adds to the currents that were originally read from one side of the transformer. This issue will be addressed by setting a fixed value for the differential. This value is higher than all the currents we mentioned, which include the magnetizing current plus any charging current in the cables, plus the maximum possible ratio error between the two sides of the transformer. Therefore, as long as the load on the transformer is from 0 up to this point, it requires the differential quantity to exceed this value for the relay to operate this value. Very nice. Okay, when we move on to the second stage, as we progress, which involves a gradual increase in these currents or other currents, and subsequently what will further happen to this in the process. It will appear more prominently as a result of what? As a result of the increased load you have. Therefore, this will require you to raise the value, and it has different writings. Similarly, in the case of heavy load and external voltage, the ratio error will increase significantly, in addition to the possibility of CT saturation for one of the CTs only, while the other CT will not be saturated. This will create a very large difference, and the transformer's response will also be planned by raising the differential value significantly. Okay, from this value to that value, as the currents increase, the ratio error increases. This happens gradually. For example, in this area, if you have currents at this value, it represents a certain value for you here. I will find that the differential reaches its maximum possible value at, for example, the point where I am standing. Therefore, the differential value is slightly higher, which is a very nice thing. However, with low currents here, when the highest possible differential is at a point like the one I am standing at now, the differential setting value will be higher by this entire amount. This means I have lost my sensitivity. Similarly, in the case of heavy load and external voltage conditions, the idea of using duo steps for the differential should be consistent throughout the entire load range from the initial value to a higher value like this. Of course, this will cause the relay to lose its sensitivity. So what should I do? Quite simply You should also gradually increase the differential setting until you reach the end of your load area, and similarly in the other area. Therefore, you create a slope to cover these points, and then you create a higher slope, because in the case of heavy load, you have a higher ratio error and also the possibility of CT saturation. Thus, you increase the slope to a higher value, even more than the first method. Then, when we reach a certain value, we implement something called differential unrestrained. Finally, we have a differential minimum value, which is the lowest differential value in your protection system. This is applied only in the case of no load and light load conditions. Then, in the case of load and overload, the slope increases gradually over time. This operating condition. And of course, where does it start from? It starts from a point or begins above, or its beginning is at the I differential minimum. Then after that, the slope is higher than the previous slope. This is because the issues you face in heavy load and external fault conditions are not just due to seat ratio errors increasing significantly, but also the possibility of seat saturation. Finally, you have something called differential unrestrained. Differential unrestrained. And with that, we have seen the general shape of how it works. Now there's also a very nice part that I like to talk about because some people don't pay attention to it. If I were to ask you now, where is the tripping characteristics of where is the tripping area or tripping region in the relay? Everyone will say that any area above this part is considered the tripping region, and all the area below is considered the restraining or blocking region. I will tell you that this is not correct. Let's assume, to make it easier for ourselves, that the bias current is a sum of algebraic currents. Very nice, that's great. Now what will be the maximum value of the differential when both currents have an angle of 0, meaning they are combined together algebraically? And the restraining is essentially the algebraic sum of the currents. Therefore, the maximum value of the differential is the algebraic sum of the currents. And similarly, the restraining is the algebraic sum of the currents. In this case, you will find that you have the differential and restraining values are equal, meaning you are definitely on a slope of 45 degrees. This means that if the restraining equation is simply the algebraic sum of the currents without dividing by 2, in this case, you have a slope of 45 degrees, you will never be able to find a tripping region or a tripping point at this point. You will never find a tripping point at this point. Why? Because the differential quantity will never exceed what? It will never exceed the restraining quantity according to the calculations we are discussing. Therefore, the operating region becomes the area between your characteristics and a slope of 45 degrees. But when does this apply? If the bias is the algebraic sum of the planes, not the algebraic sum of the planes divided by 2, because if it is the algebraic sum of the planes divided by 2, it will be a different method with an angle of something and 60 degrees, depending on your equation, of course. Very good. Now there was a term mentioned in front of us, which is the differential unrestrained. Who is this differential unrestrained? Since we didn't pay attention, let's take a look at it together. The difference between restrained and unrestrained differential now is that it tells you that in transformers and shunt reactors, you have high short time magnetizing currents. These are currents that appear during the powering up of the transformer, which we call inrush currents, the transistor, which we call the inrush current. These currents enter the protected zone or are drawn on one side of the transformer and do not exit from the other side. Thus, they appear to you or result in a situation as if one side of the transformer is feeding or passing through voltage currents. This is the first case. The second case is that during or in certain situations, you also have currents being drawn on one side of the transformer due to an increase in load or something like that, which is very good. You also have currents being drawn on one side of the transformer due to an increase in load or frequency, which is very good. Alright, so here we can say that the restrained differential which was represented for me by the differential minimum, slope 1 and slope 2. This restrained differential, number 1, its differential quantity operates based on the restrained quantity. What does that mean? It means that as the value of the restraint changes, the value of the differential changes as well. Number 2, the tripping that comes from the relay gets blocked in the presence of harmonics in the currents, which we will learn about in detail later, God willing, when we discuss the concept of even and odd harmonics that appear in the transformer during the inrush or during the overexertion. As for the unrestrained differential, as is clear from its name, means that if the value of the differential exceeds its threshold, regardless of the value of the restraint quantity or the presence of harmonics, it is not affected to the extent that it tells you that this stage can operate and give results, even if it appears in the outcome through what is present. Meaning, if you have a certain amount, it results in what can be translated as an inrush condition. That group in resistance assistance led to the existence of coordination, resulting in a second coordination that can be translated into resistance assistance. It is a coordination condition. Also, the unrestrained differential will operate normally and will not be blocked. Additionally, there is a very important piece of information about the unrestrained differential. This unrestrained differential, also known as fast tripping, uses the fundamental component of the differential current and also uses the instantaneous values. The fast tripping specialization uses the open equation of the unified horn and also uses future states. Why does it include the instantaneous value? To perform processing faster, to ensure fast tripping, even if attenuation occurs through current transformer door saturation. And something very important, what is it? It is the result of the DC offset after fault inception in the unrestrained instantaneous value differential. The DC offset after fault inception. This instantaneous value, or the unrestrained instantaneous value differential, yes, in some cases, not all, it needs to make sure that its value reaches, meaning double the value you set, just to take into account the issue that arises with you. The same detail that appears to you after the fault inception. Therefore, we can generally say that your differential characteristics, which consist of minimum, slope 1, slope 2, and so on, are values higher than or the sum of the errors you had, whether it was transformer magnetizing current mismatch or fault current due to the CT ratio and transformer tap changer. Assistance or transitional assistance due to the CT ratio, transformer tap changer plus this CT fault. It's as if you have combined all these steps into one curve and covered all these steps, and with that we have generally understood the transformer differential characteristics in numerical relays and have seen the transformer differential system.